Good evening. Welcome to the 8th annual Marin Academy Research Collaborative Wildcat Colloquium. Thank you all to our in-person audience here as well as to our Zoom audience at home. Thank you so much for tuning in. We are here to celebrate the accomplishments of our 8 independent STEM research scholars who have spent the last 2 years working on projects that I'm so excited for you to get to hear about tonight. I'm Amy. I'm the Marin Academy Research Collaborative Coordinator, or MARC coordinator. So the MARC program supports students in developing skills and literacy in scientific research, and then applying that knowledge to contribute to real-world research in their STEM area of interest. So they all choose their topic areas, and they work in partnership with the broader scientific community. So we're in for a very exciting night. As I mentioned, these students have been working for 2 years, so they started in their junior year. I just want to give a quick shout out to the junior MARC students here in the audience. Can you raise your hand, give a little wave? So these students are wrapping up their first year in the MARC program, and 1 year from now, you can come right back here and see what they have done for their projects. All right. There are many people who support students and ensure that these projects come to fruition. Each student will acknowledge the specific people that have been particularly impactful in supporting their project, but I want to give some general acknowledgements. So first and foremost, to the mentors, these are the professional scientists who volunteer their time to work with our students and help mentor them through these research projects. So thank you to the mentors here and on Zoom, and those that are not able to make it as well. Thank you to all the family and friends of our independent STEM research scholars. The 2 years of working on one thing can be a pretty tough go. And yeah, family and friends are a huge part of helping support students through this process. So thank you. The MA community broadly and the MA administration is supportive of this program. It's one of MA's signature programs, and we're truly appreciative of that support. The MA science department and Ellie, the science department chair, both in and out of the classroom, are helping support these students in their research and scientific growth. And they're also here tonight making everything run smoothly. So you'll see members of the science department here helping out in lots of ways, and they'll have name tags on so you can chat with them at the break. Thank you to Dr. Emily Willingham, who I believe is here somewhere helping make things run. She worked really closely with this particular cohort of students this year while I was out on family leave, and had a big impact on their projects. Also to Story Oates, who originally launched the MARC program, I guess 8 years ago, before I came here to MA, and really shaped how the program has grown over the years. So on that note, thinking about all of this amazing support, facilitating student research at this high level in high school requires a lot of support, and I want to extend an invite to you. If you have ideas, connections, if you yourself are a scientist, or you can think of other ways to help grow our program so we can continue supporting and empowering these students to contribute to real-world scientific discovery, please reach out. You can find me on the MA website or chat with me today during the reception. I'd love to connect. So tonight we have an incredible lineup of scholars for you to learn from. Each student will present for approximately 13 minutes, leaving 2 minutes or so for questions. So as you're hearing these talks, you can think about any questions that you have or curiosities you have about their work or their process. Please hold those questions till the end. There will be time for questions, hopefully. So hold your questions for the end, and then please jump into conversation. If you don't have enough time to get your question answered, because 2 minutes is not very long, please join us for the reception, which is in the middle. So that's a little bit tricky for the second half speakers, but please chat with our speakers and learn about their projects during that reception. If you are on Zoom, you can drop questions into the chat really at any point. So through a talk, and then Ellie, our science department chair, will be reading out those questions, raising her hand and reading them out as time allows. Okay, we're going to try to stay on a strict timeline here with each student starting at their assigned time. There are 2 sessions, as you probably know, one from 6 to 7:15, one from 7:45 to 9. In between, there will be a reception out in the cafe, there will be food, there will be science trivia cards, and there will be an opportunity to chat with each other, with the current presenters, these scholars, as well as the junior MARC students who are developing their projects. I forgot to give them name tags, but I'll make sure they have name tags so you can chat with them too. All right. I think, oh, and you are welcome to stay for one or both sessions, but we really hope that you will stay for both sessions. Restrooms are out the door to the left, this door to the left. Let's see, there's another emergency exit over here, as well as the way you came in. And I believe that's all for the nuts and bolts of the night. So without further ado, I will hand it off to our amazing student scientists to tell you about their research projects. So give me just one moment to switch us over here, and you will hear from them shortly. I am thrilled to welcome up our first speaker tonight. Mona Moshashai will be sharing her project, Effects of Sleep Loss on Anxiety and the Role Gender Plays. This was work done in collaboration with Dr. Eddie Ben-Simon from UC Berkeley.
Hi, everybody. As Amy mentioned, my name is Mona Moshashai, and I am looking at the effects of sleep loss on anxiety and the role that gender plays in this sleep loss-induced anxiety. So, as I get started, I have a question for the audience. I was wondering who here, by a show of hands, sleeps on average 8 hours or more per night? Yeah, that's great. That's awesome. On average, Americans actually sleep 6.8 hours per night. And the recommended number of hours per night varies based on age and individual sleep quality. However, adults should be sleeping between 7 to 9 hours per 24-hour period. 8 hours is optimal. A lack of sleep is detrimental to all humans. Those with insufficient sleep are 2.5 times more likely to have diabetes, 45% more likely to have a heart attack, and more prone to high blood pressure, heart disease, and stroke. So how does my project fit into all of this? I came into MARC with a general interest in sleep medicine. I read a lot of literature that focused on physiological effects of sleep loss. Something that I noticed, though, was that there were fewer studies that identified the psychological effects of sleep loss, such as depression and stress levels. And even fewer studies looked at the relationship between sleep loss and anxiety. And as I continued reading, I discovered that current research points to disparity in sleep for women. There is an unmet need to improve quality and duration of sleep, leading to an increased risk for sleep-related health diseases and illnesses. And current literature analyzing gender-related sleep differences is extremely limited. Thus, my desire to create a study that analyzed the effects of sleep loss on anxiety while also identifying the sociological gap in gender-related sleep differences was born. I hope to contribute to the current literature that calls for more research into the relationship between sleep and anxiety, as well as sleep and gender. So this led me to my research question, which is, how does sleep loss affect sensitivity to anxiety, and does gender play a role in this sensitivity? Oh. And my hypothesis based on this research question is, if participants experience a deprived night of sleep, then they will experience an increase in anxiety sensitivity because sleep deprivation worsens emotional regulation. So moving into data collection, this right here is the State Trait Anxiety Inventory, STI. It's used to measure trait and state anxiety. It's used in clinical settings to diagnose anxiety as well as differentiate it from depression or other depressive syndromes. So there are 20 items that evaluate state anxiety and 20 items that evaluate trait anxiety. So what are the differences between the two? State anxiety is a temporary situational feeling of worry or nervousness, while trait anxiety is a personality characteristic that would predispose an individual to experience anxiety in many different situations. So our study only utilized the state anxiety survey because that is the emotion that changes and result to external factors. For us, it was poor sleep. So all of these statements are rated by participants on a scale of 1 through 4, indicating how they feel in the exact moment that the study is administered. 1 corresponds to not at all, 2 corresponds to somewhat, 3 corresponds to moderately so, and 4 corresponds to very much so. So the statements range from I feel calm to I am tense to I feel strained. And as you can see, not all of these statements here are negative. So not all of them correspond to an anxiety score. So for positive statements, there's a formula to derive an anxiety score. And to do that, you subtract the original score that the participant has written by 5. So for example, if a participant were to rate I feel calm a 2, you would subtract 2 from 5, and the anxiety score for that statement would be a 3. So, moving into my process and methods, I connected with my mentor, Dr. Eddie Ben Simon, a neuroscientist who works at the Walker Lab at the University of California, Berkeley, in the spring of my junior year. We had our project outlined by the end of my junior year, and the summer between junior and senior year was my onboarding process in which I had to complete to be able to work at the Walker Lab. So together we decided that we would utilize data from 4 different studies from UC Berkeley that Dr. Simon had been a part of. So the dates range from 2013 to 2022. And across these studies, there are a total of 100 participants, 47 female, 43 male, and they're aged 18 to 30 years old. So it's important to note that these studies had unique objectives from our own. However, each had conducted the STI state survey, which I mentioned on the previous slide, and this was what we used as our raw data. So across the study, participants did not have a history of sleep disorders. They sustained a normal sleep-wake cycle of 7 to 9 hours per night for at least 3 nights before the test. They abstained from caffeine and alcohol 72 hours before the test. They had no history of neurological disorders, no open or closed head injuries, no psychiatric disorders, or use of antidepressants, psychostimulants, or hypnotic medications. And so each of these participants came into the lab for 1 night of rested sleep and 1 night of deprived sleep. So a night of rested sleep would be an 8-hour period of uninterrupted sleep, and a night of deprived sleep would be a night where the participant is woken up every hour. And so every time a participant awoke, whether it was naturally or artificially, they filled out a STI state survey to indicate their current emotional state. And this contributed to their total anxiety score for a time point and session. So sleep deprivation is equal to SD and rested sleep is equal to SR. And so at each time point that a participant filled out a survey, we had given it a number that would correspond to an actual time. So for example, time point 1 would correspond to 8 p.m., time point 2 would correspond to 9 p.m., and so on and so forth. And that's universal across all the participants and data that we looked at. So moving into my senior year, I digitized all 4 studies and reorganized them into Excel. So again, our data was just looking at those self-assessed surveys, the STI state assessment. So the data here, here are the 11 columns that it's organized into. And to give a little bit of context, there's over 26,000 rows of data. So that means that there are 1,300 surveys that were digitized. So this is one survey, an example of one survey for a participant at one time point. So the statements are on the left, and then the ratings are on the right. And then this is what the raw data now looks like in Excel. And so we analyzed how SD and SR sessions compared in terms of total anxiety, and we analyzed how gender played a role in an emotional reaction to a lack of sleep. So we utilized both Excel and Python to analyze data and run statistical analyses. So overall, I was interested in learning about how participants' anxiety levels differentiated between the sleep rested or SR treatment and the sleep deprived or SD treatment. So one high level way to look at this is just to average the corrected STI scores across all time points, which is a graph of what I'll show you first. So here for my first graph, we took an average of all participants' final scores across all time points across both sessions. So on the x-axis, we have the sleep deprived and the sleep rested. And then on the y-axis, we have the average final anxiety score. It goes from 0 to 4, just like on the survey. So there's a slight difference between the SD and the SR average final score values. However, it is not as distinct a difference as we previously believed there would be. However, we did run a t-test on this specific data set, and the p-value we received was far less than 0.05, so the data here is significant. However, this is a very straightforward way of looking at our data, and we found that the story got a little bit more interesting when the data was organized in more nuanced ways. So slightly more nuance here. We have the x-axis separated by gender. So we have female over here, male over here. And then we have the blue bars corresponding to sleep deprived and the orange bars corresponding to sleep rested. And then similar y-axis, average final anxiety score. So what we did here was we took an average of all participants' final scores across all time points across both sessions. However, what we did was we differentiated by gender. So here there's a slightly more noticeable difference than the previous result, and these results indicate that female participants may have been more sensitive to sleep disruption than male participants. and it supports the theory that gender-related sleep differences do exist, and women may actually be more likely to experience an increase in anxiety levels following a night of poor sleep rather than men. So for this figure here, we wanted to analyze data at specific time points in order to compare this difference in points across sessions. So for the x-axis, again, we have sleep rested and sleep deprived. And then the colors here, the dark blue signifies night, and the orange color signifies morning, and then the y-axis is the same as the previous two figures. And so what we did was we picked time point 3 for the nighttime, and that corresponds to 10 p.m. And then we picked time point 14 for the morning value, which corresponds to 9 a.m. And all participants had survey data for these two time points. So we compared the differences between night and morning anxiety across sessions, and we noticed a slight increase in SD session levels than SR session levels. And it's interesting to note actually that the SD session started off with a slightly higher anxiety score than the SR session, and the SR session had a slight increase in anxiety scores, which is not something that we were expecting. And these scores, again, are not as distinct as we previously believed that they would be. So moving into discussion and implications, what we learned really was that there are many ways to cut the data, and it is a lot more complicated than average final scores across sessions. And this is partially because the data set is so big. And there were limitations to our study. It was self-assessed data. The studies were conducted in different time periods and for different purposes than our own. And it's not a very diverse sample, as all participants were undergraduate or graduate students at UC Berkeley. And the differences in our data are small, but they are there. Even though they're not huge, there is some preliminary data suggesting that this is worth looking into on a bigger scale to see if the pattern plays out in a more meaningful way. So what we did take away was that there was a significant relationship between sleep loss and an increase in anxiety, and a noticeable difference between scores across genders and time points. So what this really calls for is further research and resources to be put towards not only understanding the psychological and mental effects of sleep loss, but also why gender-based sleep differences exist and how to bridge this gap so that everyone is really getting the quality sleep that they deserve. So moving forward, we're also interested to see if sleep can actually restore anxiety levels. So looking at it from the other way and seeing if it can aid emotional regulation. And then we are also interested in seeing if people with a baseline higher anxiety score, so looking at that trait data versus the state data, respond differently to a lack of sleep rather than people with a lower baseline anxiety score. And we're also interested in using EEG or MRI technology to better monitor brain activity following a night of rested sleep or deprived sleep. And for my acknowledgements, thank you to Amy Strauss, Dr. Eddie Ben Simon, Dr. Emily Willingham, James Westphal, Jillian Hinaka Ozawa, John Breton, my dad, and the MARC class for all of your support throughout the past 2 years. It has meant a lot and has been super, super helpful. We have time for questions. And if you have further questions that don't get answered, or you just are interested in the data and have ideas about what you might want to do with it or what you think could be done with it, here are some ways you can reach me. You can also find me, like Amy mentioned, during the intermission. Thank you. Yeah, so I believe the Walker Lab has done some work with EEG technology. However, it was a limited study, and therefore it didn't fit into our sample. And so there weren't enough participants for us to pull data from. But that's something that they've done, and I definitely think it's something that they're continuing to work on in the future. Yes.
Do you have a favorite moment or conversation with either your mentor or with your knowledge, or just something you like process?
That's a good question. I think for me, there were definitely a lot of learning curves with Excel and Python. So I think like it was definitely very satisfying when I like created a figure that analyzed like the things that I was actually looking for. That was definitely super satisfying. I would say connecting with my mentor was a really great process, and kind of finally like finalizing someone that I could just reach out to about my data and who really understood what I'm looking at, and could kind of aid me along the process. But yeah, I would say those two things as well. Just like support from everyone has been super rewarding, and seeing how much people care, especially like lab members, like the lab manager and the RAs at the lab I worked at, seeing how like helpful and how much they cared about investing into a high school student who's doing research was really, really satisfying as well.
Thank you, Mona. Great. Thank you, Mona. Next, we're going to hear from Kalen Blodgett, who will share his work identifying the optimal layout of the Elise ITS-3 using machine learning. This was work done in collaboration with Dr. Nicole Apadula from Lawrence Berkeley Lab.
All right, so hi, my name is Kalen, and as Amy said, this is my research presentation on identifying the optimal layout of the Elise ITS-3 using machine learning. So the bulk of this presentation is going to be the context for my research. So before we dive into that, I'm going to just give a brief overview of what that's going to look like. So first I'm going to cover the Large Hadron Collider and the Elise experiment. I'll talk about what the quark-gluon plasma is, the objective of the Elise experiment, the internal tracking system of this Elise experiment, and then where I fit in. Then we'll briefly cover machine learning and the different parts of ML, which is common abbreviation for machine learning, and then how I'm using it. So to start, the Large Hadron Collider. It's the world's largest and most powerful particle collider. It's located in both Switzerland and France, and it's built 100 meters below ground, and it has a 27-kilometer circumference of the ring that it's made up of. And it was built to do research in particle physics, which is a field that remains full of mysteries to do with the birth of the universe and the building blocks of our world. So the Large Hadron Collider tries to answer these mysteries by taking particles and accelerating them around that 27-kilometer ring, and then smashing them into each other and figuring out what we can discover from that. Which is in fact quite an effective method of research and has yielded many, many results since it became active in 2008. This is work that I've been doing in collaboration with my mentor, Dr. Nicole Apadula, at the Lawrence Berkeley National Laboratory, which is one of hundreds of institutions across the world that is contributing to the Large Hadron Collider. It's a really large collaboration, and having so many contributors has allowed it to be at the forefront of particle physics research since it became active. So, the LEIS experiment, which stands for a Large Ion Collider Experiment, is one of 9 experiments that each have their own specialized detector situated around the Large Hadron Collider. And the ELISE experiment is designed to study a specific phenomenon, that being the quark-gluon plasma. So first, what are quarks and gluons? So quarks make up protons and neutrons, which in turn make up atoms, and they never exist alone. They're always bonded together by what are called gluons. And this bond between quarks and gluons is extremely strong. Only in the most extreme of conditions does it break apart. And when I say extreme, I mean 4 trillion degrees Celsius. So this state where the bonds between quarks and gluons break apart is what's called the quark-gluon plasma. And it's got some very interesting properties. It behaves somewhat like liquid, but there's a lot of properties that we still don't understand about it. And so for the first 100 milliseconds after the Big Bang, the universe was filled with this quark-gluon plasma. And after it cooled, it formed everything that we now know as the universe. So it's very important to understand the properties of this state to understand the evolution of our universe and for furthering our knowledge of particle physics. So how does the ELISE experiment research this? So it attempts to create the quark-gluon plasma by taking super heavy lead nuclei, accelerating them and smashing them together, which it allows them to achieve this quark-gluon plasma state for just a few fractions of a second, in which the detector can look at that collision and see how the quark gluon plasma expands and cools. So looking at the ELISE timeline, it became active in 2010. Since then, it's had its first detector upgrade. These upgrades allow the experiment to adapt to better technology and remain at the forefront of research on the quark gluon plasma. And you'll see there are these runs. Those runs are when the detectors are taking data. The detector will be currently active during those stages. And then you have these LS phases. LS stands for long shutdown. During these phases, the data that's been collected is being analyzed, and the detector is also repaired and upgraded. So right now, we're at the tail end of run 3, and my research is looking ahead to the long shutdown 4, which is when the ELISE 3 detector will be installed. So the ELISE 3 detector is much more advanced than the ELISE 2 in many ways. The area I'm focusing on is the internal tracking system, which can be abbreviated to the ITS-3. So the internal tracking system is going to be located at the center of these detectors, and it's the closest tracking device to the location of that initial collision between the lead nuclei. So because of that, its objective is to pinpoint those locations of the initial lead nuclei collision, and then track those initial paths of particles as they explode outward from the collision. Compared to the current ITS-2, ITS-3 has twice the precision when determining the trajectory of a particle, and it's also ultra thin, around 50 micrometers. So because of these technological advancements, there are both pros and cons when designing for it. So in terms of pros, its lighter weight allows for air cooling, whereas previous tracking systems had to use liquid cooling, which significantly reduces material budget. Better precision can also be achieved both through geometric and technological improvements. In terms of cons, it's intensive and costly to produce these sensors. Machinery to produce these sensors must be custom made, and so producing the sensors with different sense of dimension would require even more custom built parts, which, because we're on a budget, is not really ideal. So this means we're constrained to building the ITS-3 with sensors of a fixed singular set of dimensions. What I mean by that is our objective is to fill these disks as much as possible. We're trying to optimize coverage of these disks. And that's difficult to do when we're working with sensors that are rectangular. The best way to optimize coverage would be to reduce the size of these rectangles as much as possible. But that would also bring costs up significantly because it would mean more production. So it's just not ideal to have such small sensors. So the ultimate goal is to find a balance between cost and performance. Performance is going to be directly tied to the coverage that we can get of these disks. So to recap, we have the ELISE experiment, which is researching the quark gluon plasma because it can help us learn about why our universe has evolved in the way that it has. This has to be done using precise technology that is always being improved, hence the ELISE 3 upgrade, and the new ITS-3, which is good for scientific purposes, but difficult to design for. So let's break down this problem. This visualization that I've been using was created by an algorithm that generated coordinates that we could then map to this disk when given a sensor of dimensions 19.2 centimeters by 10 centimeters. These black strips you can see here are the inactive regions of the sensors, which is where the sensors will process the information they're receiving from the active regions, which are in green. Disks will all have this inner radius where the beam of particles is going to pass through, and no sensors can be placed there because you wouldn't want to, get in the way of that collision happening. So this algorithm that was used is something called a dynamic paving algorithm. It can generate coordinates in a very specific way and requires some hard-coded elements to function with each new set of dimensions. So it's a good start, but we need a way to show definitively that a certain set of dimensions is optimal for both coverage and cost, which can't easily be done with this algorithm because it would require kind of guess and check to answer this question. So that can't easily be done with this algorithm. which is why we're going to turn to machine learning, which is robust, flexible, and scalable. In essence, it's going to do the same thing. It's going to give us an algorithm that takes our inputs, which is that set of dimensions that we want the sensors to be, and it's going to give us an output of a set of coordinates that we can then map to those disks. But the way it processes those inputs to get to that output is going to be much more complex than that algorithm that we were using previously. So I'm going to cover the four main parts of machine learning that are relevant to my project. It'll be covered in more, machine learning in general will be covered in more depth in later presentations, but I just wanted to give a quick overview of the parts that are relevant to my research. And I've also included some screenshots of code that I've written just to show how I've realized these different parts, but it's not important to actually read what I have on that code. So to start, we have the training data. In essence, this training data is going to allow the model to learn patterns and then generalize it to any other dimensions that we try and give to it. Then we have the model structure, which is going to determine the complexity of this model. You can think about it as neurons in a brain. The more neurons there are, the more complex the brain is. That's essentially what the model structure is. Then we've got this loss function, which is going to give the model direction during training. It's going to tell the model if what it's doing is good or bad by returning a certain value. The higher that value is, the worse the model is performing. Then we get to the training step, which is the culmination of these three previous steps. We've tried to be as specific as possible for the model as to what we want its goal to be. And now we just have to try and let it learn about that said thing. So after putting together all of these things and working for months to optimize different parts of this design, my model was able to produce this. So let's discuss. Clearly, it's not exactly ideal. There's a lot of overlap between the sensors, and it's completely ignored that inner radius where there shouldn't have been any sensor splits. So why did it take so long to create a model that can only do this? Similarly to how my presentation was mostly context, a lot of my work within MARC was mostly skill building. So there was a very steep learning curve to get to where I am today, a lot of guesswork. And fortunately, I'm at a place where I'm kind of past the hardest part. So where this is where I'm going to have to leave you today, this isn't where I'm going to leave this project. I'll continue working on it over the summer, and now that I've gotten through the most difficult part of learning this stuff, I will easily be able to modify this model. I know plenty of different directions I can go to make this look better. But yeah, it was just a steep learning curve to get to where I am today. And when I'm done with it, I can also hand it over to my mentors. They can continue to optimize it. And once we have that strong model, we'll be able to identify that optimal layout by analyzing a wide variety of different factors. And then it'll become part of the ITS3 design, and we'll see results in about 10 years' time. So acknowledgements. Thank you to the MARC class, Amy, Dr. Emily Willingham, Dr. Nicole Apadula, and Dr. Rita Sadat. With that, questions?
One question is that you mentioned that the input slightly more the parameter instead of the web not optimal.
Sure.
Cause that difference between the actual. If you have any idea what the optimal is, or you maybe you don't want it because of time you don't want to present here, but do you have a path forward?
Yeah, so I can't, I don't have a straightforward answer of what the optimal dimensions would be. The path forward, it's not only going to be determined by the actual like geometrically optimal solution. There's not only cost considerations, but also like production considerations. There might be things that are just not physically capable to be designed. And there are already some like standardized dimensions that we've been considering, like creating dimensions that are only by a factor of 3.2 centimeters. So you'd have a sensor that's like 3.2 centimeters by 3.2, and then you go up to 6.4 by 6.4. And so you'd continue by that increment to find what of that concrete increment would be the best. So there have been some things that are already standardized to work with production. So that's one way forward, but yeah, I can't give you a straightforward answer right now.
What was the evolution of you coming to this particular project? Like, what did you start out being particularly interested in this, or did you start somewhere else?
Yeah, so when I connected with my mentors at the end of junior year, they were broadly working on the Elise 3 ITS upgrade. So I knew my project was going to be with ITS 3. But in my senior fall, I took a class on machine learning and AI in Python, which allowed me to very easily transfer those skills that I learned into my research here. If I had not gone with that class, I could have gone through a more like hardware approach rather than looking at optimizing design. I could have been maybe looking at the actual hardware that's being used for the design. But yeah, it was a combination of what my mentors were doing and the skills that I were picking up and the things I had interest in.
Thank you, Kayla. All right. Thank you, Kaylin. Moving forward, we will hear from Jasmine Wood, our next speaker, on her project Image-Based Profiling for Proteostasis Modulators. This was work done in collaboration with Dr. Brian Hodge from UCSF.
Yeah, so as Amy mentioned, my project is called Image-Based Profiling for Proteostasis Modulators. And I know that sounds really complicated, but I promise I'll explain that all to you guys. So first, let's start off by defining biological aging. So biological aging is the gradual accumulation of damage to cells and tissues within the body. And a key hallmark of this biological aging is a gradual decline in proteostasis or protein homeostasis, which is the cellular processes that maintain proper protein folding, localization, and degradation. So age-related losses in proteostasis can cause the accumulation of misfolded proteins, which ultimately manifest in Alzheimer's, Parkinson's, and Huntington's diseases or other neurodegenerative conditions. So understanding how and why this protein homeostasis declines with age is super important for developing effective treatments for aging and aging-related diseases. So with the rise of automated microscope imaging, complex image analysis software, and machine learning models, high-content image analysis is coming to the forefront as a powerful research tool for analyzing cell health readouts and biological responses to novel drug treatments. So the integration of this high-content screening data and advanced computational techniques can accelerate the identification of novel therapeutic candidates and quickly assess their potential for clinical application. So over the past year, I've been working with Dr. Brian Hodge, a research specialist at the Geswicki Lab at UCSF's Institute for Neurodegenerative Diseases. The Geswicki Lab focuses on understanding age-related changes in the proteostasis network and identifying therapeutic targets to restore proteostasis in aged cells. And Brian's work focuses on investigating the interplay of environmental and genetic factors in aging and longevity. So the goal of our project was to use cellular image data of cells of various ages to identify drugs that restore proteostasis in aged cells and delay aging. And this involved extracting morphological or structural features from images of healthy young and old cells to train predictive models for cellular aging and homeostasis decline, or image-based aging clocks. These clocks were then able to screen a library of small molecule proteostasis regulator compounds to evaluate the impact of candidate drugs on cellular aging, while also reporting on the activity of different arms of the proteostasis network. My research was focused on building these custom processing and analysis pipelines for the high content imaging and drug discovery. So first I'll go over on how we acquired these images to later analyze them through our models. So in order to observe the different organelles and subcomponents of the cells, cell painting assays were performed. So after the cells were treated with their respective candidate drugs, they were stained with 6 fluorescent cell painting dyes to label different cellular components, and then they were imaged with an automated microscope. And you can kind of see that in the slide here. So these components included the nucleus, nucleoli, mitochondria, endoplasmic reticulum, Golgi apparatus, actin filaments, and cytoplasmic and nucleolar RNA. And we'll later use algorithms to pull out these features from these 5 different cell painting channels. So because we don't know yet what features will be important, the cell painting assay allows us to measure everything first and use computer algorithms to ask questions later, hence it being an unbiased approach. So next we'll move on to the feature extraction part of the analysis pipeline. So using the raw microscopy images of the stained cells, we then performed an image correction step to correct uneven illumination and shading, and then used a software called Cell Profiler to segment each individual cell from the raw pixel data of the cell painting dye channels. And this was to extract biologically relevant phenotypic or observable features from the images. This process generates single-cell profiles containing over 4,000 quantitative features, including measurements of morphology, intensity, texture, and spatial organization of the labeled cellular components. So we measure a lot of features, but not all of them are important. Some are very redundant. And in order to increase the signal-to-noise ratio and focus on the important features rather than unnecessary information, we need to further process this data, and I'll show you how that improves the downstream tasks. So we've measured everything at the single cell level, which is 4,000 features per cell and thousands of wells. That's way too much data. So our first step is to aggregate the data into a single profile per well. And then we try to remove plate level batch effects by normalizing all the features across a plate. Now, we still might have too many features, so we perform a number of feature selection steps to remove unnecessary or repetitive information and noise from our data set. And since we've done multiple experiments, we need to remove experiment level batch effects so that we can compare data across these different plates and experiments. So here is a metric of how well our pre-processing steps worked. So as you can see on this graph, the x-axis is MAP, or mean average precision, which assesses how similar or different the features from the compound-treated replicates were from the negative controls. And on the y-axis is negative log p-value, and that might sound a little complicated, but p-values are used to determine if a result is statistically significant, and taking the negative log of these values makes those smaller values easier to compare. So the smaller the p-value is, the more statistically significant a result is, and the larger the negative log p-value is. So the higher numbers are more statistically significant. And we used a statistical approach to see which of these compounds induced a signal that was different from the control, and we call those compounds phenotypically active. And that's all these compounds above this line right here. So these compounds have notable observable effects on the cells compared to a control, and that would be, any compounds above the line, and the compounds in the bottom, we couldn't really distinguish a difference from the control. So we compared the effects of using just the raw image data, the feature selected data, and the spherized data that went through the full image analysis pipeline. And with the raw features, we only calculated about 16% phenotypically active, and for the feature selected data, we calculated about 33%. And that's a huge jump to 69% for the phenotypically active compounds using the feature process data. So this demonstrates the robustness of our image profiling approach. So now we're going to use those images of the different cells to train a model that can accurately predict cell age of different compounds. So in order to account for the different states and ages of the cell, we treated our model using this Google cell painting dataset, which looked at data from cells of various ages and disease states, particularly looking at Parkinson's disease. This paper looked at human primary fibroblasts, which are skin cells taken directly from a person. And now for our results. So we used an elastic net model to predict cell age, and an elastic net model takes all our features and the corresponding ages of those features and learns to recognize patterns of how to weigh the features to determine which are and aren't important in predicting the cell age. So along the x-axis is the actual age, and along the y-axis is the predicted age. And we split this into a training data set and a test data set, and we train the model on the images that are shown on the left, so it makes sense why that's more accurate because the model learned from that data. And the model hadn't seen the samples that we used with the test data set, so obviously it's not perfect, but there still is a pretty strong correlation. So after we trained the model, we asked it to predict the age of cells treated with the proteostasis network compounds. And these are the individual prediction data points for the compounds on the x-axis, as you can see here. And the y-axis measures the age delta, which is the difference in predicted compounds compared to the control treatments that the model predicted. So the model identified 7 treatments that significantly reduced the predicted cellular age, including dexamethasone, and 3 compounds that significantly elevated the predicted cellular age, including apalimod. Notably, dexamethasone treatment has previously been shown to cause cells to behave younger, and apalimod is known to disrupt the function of the lysosome, which breaks down waste in the cell and thereby drives cellular aging. So these findings further suggest that disruptions in proteostasis play a critical role in driving cellular aging and these findings also highlight key drug treatments that could offer potential therapeutic strategies for age-related diseases like Parkinson's disease. We can also take more of a biased approach and instead of cell painting, use NT-pan-MI, a dye that labels unfolded proteins, which is a hallmark of disrupted proteostasis, as I mentioned earlier in the presentation. So an increase in fluorescence of this dye is indicative of higher protein unfolding load, suggesting that treatments interfere with proteostasis pathways or induce stress conditions that disrupt protein folding. So in these images, the cells on the left show higher levels of unfolded proteins, indicating impaired proteostasis, which makes sense because the compound, EACC, blocks proper protein degradation. Whereas the cells on the right are treated with dexamethasone, which have a lower fluorescent and suggest that fewer unfolded proteins and more stable proteostasis. And this is in alignment with our result from the previous slide, identifying dexamethasone as a top anti-aging hit. So we trained a model that can predict protein unfolding using this dye and cell painting features together. So as you can see, we compared the predicted NT-pan protein unfolding signal based solely on the phenotypic data from cell painting to the actual protein unfolding signal of the cells. So the R-squared tells us how well this model fits the data, with an R-squared of 1 being a perfect fit and an R-squared of 0 indicating no fit. So having a score of 0.77 is pretty good and shows that we can predict compounds that increase protein unfolding with pretty strong accuracy. And we use the second model to predict protein unfolding over time in both healthy individuals and those with Parkinson's, a condition known for increased protein aggregation. So as expected, both prediction graphs show a rise in protein unfolding with age, which is consistent with the general decline in proteostasis during aging. However, the disease group's trend line not only follows this upward pattern, but also starts higher at the y-intercept and remains consistently higher than that of the healthy group. So this aligns with patterns that we know between Parkinson's and impaired proteostasis and reinforces our model's ability to capture these meaningful biological differences. So, to summarize, our image-based profiling approach allowed us to capture unbiased phenotypic profiles of cellular responses. And the feature extraction and feature pre-processing steps that we performed allowed us to improve our signal-to-noise ratio and allowed our model to focus on real biological differences, leading to more accurate and reliable predictions. A central focus of this project was the development of an image-based aging clock designed to predict both cellular age and protein unfolding solely based on these profiles. So the aging clock not only serves as a valuable biomarker for assessing the effects of compounds on cellular aging, but also facilitates deeper understanding of aging-related phenotypic changes at the single cell level. And by applying this model to a library of small molecules, we successfully identified compounds that modulate the proteostasis network and offer potential therapeutic drug candidates. This work highlights the power of combining imaging, machine learning, and biological insight to drive therapeutic drug discovery and deepen our understanding of aging at the cellular level. So these insights can open new avenues for promoting healthy aging and improving quality of life for older adults by addressing age-related neurological decline. So for some final acknowledgements, I'd like to thank Dr. Brian Hodge, Dr. Jason Yoswicki, and the Getslicki Lab, Amy Strauss, Dr. Emily Willingham, and the MARC cohort for all the support these past 2 years. And now we have some time for questions. Yeah, if anyone has a quick question, yes.
Thank you very much. It's very interesting. Do you think that this model that you present here and the applied practices, because we know that in general many diseases are related to protein that the defect in our body?
Yes, definitely. The paper that had the data set that we trained our model on specifically focused on Parkinson's disease, but we can definitely use cells that had other disorders and diseases to kind of look at those impacts. Yes.
Select candidate.
Yes, definitely.
Thank you. All right. Thank you, Jasmine. All right, for our final speaker of session 1, we have Hunter Price, who will share his work, The Role of Sleep and Pre-Sleep Habits in Adolescent Social Media Behavior, one probably of great interest to many in the room here. And this was work done in collaboration with Dr. Jamie Zeitzer of Stanford.
Hello, everyone. As Amy said, my name is Hunter, and I will be presenting my MARC project on the role of sleep and pre-sleep habits in adolescent social media behavior. So, for some background information, adolescents use social media extensively, and every year since 2014, social media use across all age groups has increased. So, it only gets more and more prevalent as time goes forward. And social media platforms are monetarily incentivized to have their users spend more time on their platforms, watching ads and doing other sort of metrics. And so this leads to a lot of addiction among adolescents who are particularly vulnerable to this type of marketing, which is why I wanted to look at social media and social media addiction. And then I wanted to look at social media through the lens of sleep. So through multiple past studies in the past 5 years, we know that poor sleep and digital are as heavily linked with digital behaviors. So being addicted to social media or even other forms of alcoholism, like alcoholism, are going to worsen your sleep quality and your average sleep duration. But I want to see, okay, if you're sleeping less, is this also going to happen with social media? That you're going to spend more time on social media. So this led to my main question: how does sleep time influence time spent on social media? video games, and reading the following night. So when you should be catching up on your sleep after you've been sleep deprived. So my main hypothesis was that people get less sleep, they're more sleep deprived, that the next night they're going to spend more time on social media than they did the previous night because they're going to feed into that addictive pathway that social media has. And this is based upon literature that has shown in the past that people, when you're sleep deprived, you make worse decisions and your reward response is inhibited because of deprived sleep. And for this study, I decided to use video games and reading as a form of a control because paid upfront video games don't have the same and reading don't have the same monetization structures as social media. They're less addicting, and so it was my thought that these two would have no effect or a much diminished effect because they're lacking that addictive thing that is causing our participants to sleep less and exchange that time for use time on social media. So this is kind of one predicted result that I had for my hypothesis that as sleep time decreases, the time spent on social media increases as sort of a replacement method for that. So for my methods, I did a survey of the MA community. I had first a baseline survey, which collected demographics like race, age, and sex, as well as daily reminders, optional daily reminders, and emails in order to track participants when they submit data. And then I had the daily survey, which is where I collected our data. I aimed, with the help of my mentor, for a 2-week station or 2-week data collection period that collected sleep timing. So when people went to sleep, when they woke up, the time they spent on pre-sleep activities, so social media, video games, and reading, and then also screen time verification. So screenshots of their screen time report to get a little bit of objective metrics of what's going on. And then also the Burgeon Social Media Addiction Scale, which is a well-known test in the social media field to a well-known survey to quantify how addicted or people's likelihood of being addicted to social media. So this is kind of a look at who we actually got in our participants. Unfortunately, we didn't get a very diverse sample size overall, but it is fairly accurate for the MA community, which is the people that I surveyed. And not only here, but the average age of each participant, the average age was around 16.5 years old, though we had people as young as 14 and slightly older than 18. And 81% of the participants we had opted into daily reminders. And we also had an incentive program. The more entries you submitted into the study, the higher likelihood you had to receive an Amazon gift card in a random raffle. But as you'll see later on, unfortunately, we did not have too much consecutive responses even with these. So this is a graph of all the participants who responded to the daily study. We had 46 participants respond to the daily study with 147 total responses for an average of 3.2 responses per person. But unfortunately, we only had an average of 1.67 consecutive responses per person. So as you'll see in the next graphs and the next few slides, all the participants here who only submitted one night of data, I can't know how they spent their time the next night. So they're not going to be able to be included in my main analysis. But I can use them to show some general results. So across the study, the average sleep time was a duration of 7.5 hours, which was actually quite good and surprised me a little bit, but which is very close to the 8 to 10 hour range that is recommended for adolescents. And participants had an average burden social media addiction scale score of 14.6, which is a range between 6 and 30, with the cutoff for severe addiction being at 24 out of 30. So there's not that much, there's not like widespread addiction within our MA community, but 14.6 is enough for a moderately concerning usage of social media for most participants. And as you can see, that's also in the usage graph here. So social media, people use social media before they went to sleep significantly more than any other metric. For mobile video games, it was only 5.8 minutes, and console gaming only 5 minutes, but sleep had nearly an hour of social media before participants went to sleep. And this is only in 3 hours before sleep. We didn't look at the rest of the day. We wanted to look at what people were doing instead of going to sleep in that nightly time. and participants averaged a total of 71 minutes of screen time within that 3-hour pre-sleep period. So this is kind of graphical representation. So as you can see for social media, there's a lot of responses that indicated spending a lot of time on social media. But for gaming, almost all the responses were zero. Not many people use social media at all. And what surprised everyone was gaming before they went to sleep. But what surprised me was that actually reading had a slight increase on both forms of video games before students went to bed, which surprised me. And then, so let's actually look at our nightly impact here. So this here is a graph of sleep time on the x-axis with the time participants spent in the 3 hours before sleep the following night on social media. And what we can observe in this trend is that as participants slept less, closer to the 4 to 6 hour mark, they spent more time the following night on social media. And this graph has been removed participants who did not spend any time on social media throughout the entirety of the study. So this is only for people who actually use social media, at least in some part of the study. But what we can see is that participants do spend more time on social media when they feel that sleep deprived, even when they're tired. Although the R-squared value, as talked about in the last presentation, which is a metric to how accurate your data conforms to the trend line, is not very high, only at 0.14. So although the trend is there, it's not significant and it's not entirely true for all participants. So this is another way to visualize the graph for social media. So here, for the data for all participants, we collected an average. We averaged out their sleep time and their time spent on social media before they went to sleep. So now this graph is looking at the averages. So what we can see in this trend line, although it's much less accurate, is that ever so slightly, when people slept below their average on a given night, they tended to spend slightly more time above their average the following night on social media. So this trend, even with looking at averages, is still there, although it's a lot weaker than the previous graph. And so one thing I wanted to look at is actually, okay, so we have this original graph, but how many people are we actually looking at? When I looked at participants who had five or more responses in some sort of consecutive grouping, 2 and 3, 2 or 2 and or like 4 and 1 or something like that, then we at this graph. So actually the majority of the points and the main part of the trend line is actually only from 7 participants. These are the people who submitted 5+ entries. And so although this trend is like quite even stronger in these participants, 0.3, we can't really say that it goes for all participants in the event committee because, again, this is only 7 participants. And so for video games, unfortunately, we can't really say anything at all when controlling for non-participants and for people and for only looking at consecutive entries. We only had 3 people who spent any time at all in the 3 hours before sleep on console gaming. So there's nothing really to say there. And we only had, I believe, 13 responses for mobile gaming. So almost nobody used gaming at all. But however, the small cluster of 15 minutes spent before sleep on mobile gaming could be a result of daily quests or daily rewards that are often in mobile video games nowadays that incentivize users to log on for a short period of time each day. And we can kind of see this here as a kind of regardless of sleep, people were spending just that 15 minutes on mobile gaming just to do just a few daily tasks. And reading, this is the big surprise, is actually reading went slightly against our hypothesis. I initially thought to include reading as a form of a control because there is like very minimal addictive habits with reading, but it actually turned out very similar to sleep, where as participants slept, or very similar to social media rather, is that as participants slept less on the next night, they almost always increase the time they spent reading. And this is only reading for fun, so not including schoolwork. This is just people who are picking up a book or an article and reading it. And I also found that was extremely interesting. And this kind of brings into question, like, is the result that we saw for social media because of its addictive habits or some other component that I'm not looking at? Because reading is also here as being a very, very similar trend, and it's not having those addictive pathways that it creates in adolescent brains. So what can we kind of conclude from this? social media is extremely popular within the MA community, and most teens have a moderately concerning relationship with it. So this kind of necessitates a little bit better education on sleep hygiene. So what you're actually doing in those 3 hours before sleep that have already been documented on, it's already been documented the negative effects. So it could be a good place to educate the MA community about what they should be doing in this sleep period before they go to bed. And with that, we have an average, our average sleep duration of 7.5 hours is slightly below the recommended daily amount for adolescents. And also, around 60% of participants indicated that they were forced to wake up, or go to bed later, earlier or later because of sports commitments or volunteer work or school work. And this can kind of highlight that there's a lot of inconsistencies in adolescent sleep schedule thanks to high school that could be participating or activities done in high school that could be participating or could be contributing to this trend that we see in both reading and social media. And for limitations for the study, again, we had a very small and non-diverse sample, only MA students and mostly female and white students who were responding to our survey. Also had a very low number of consecutive responses, which definitely hampered my ability to perform large data analysis on the group. And we also had minimal objective metrics and recall bias. So some of the values for sleep time could be a little bit off. And there's also an idea of selective reporting in this set. For the participants who only submitted for one day, it's unlikely that they would have submitted a day where they felt super tired and didn't want to respond to the survey day. It's more likely that they submitted to the survey when they felt that they had free time or a lot of sleep and felt rested and able to respond to the survey, which kind of brings into question exactly if this trend line is true for everybody, which is where future directions come in. So for the study, there's a lot of limitations, as I just said. So as going forward, I would like to see a deeper within-person analysis, which was my original goal, but it wasn't possible due to the low consecutive number of entries. But I really do think that there is something to be seen within a deeper per person level, since sleep is different for every person and everyone's schedule is slightly different. And I would also like to look at or assess a possible dose response relationships. So, okay, yes, when you sleep less, you tend to spend more time on social media. But if we actually get people to sleep better, to improve their hygiene habits, are they going to spend less time on social media? Or is that just something that people want to do irrelevant of like improving their sleep schedule? And I would also like to consider variables such as gender and economic status, as they have been proven before in other studies to impact how people sleep. And also, we could do an intervention study to actually see, like I said before, to change people's sleep and try to see if those same pathways are there even when we intervene and change the natural order of things. And for my acknowledgements, I'd like to thank my mentor from Stanford, Dr. Jamie Zeitzer, the Institutional Review Board, which had to be created this year for my project, and of course, Emmy Strauss and Dr. Emily Blenkham for helping us and helping me and my MARC cohort develop our projects. Thank you.
One. The goal, or each survey or each participant would submit what they did the day before. So the goal, or like what time they went to sleep the day before and when they woke up today. So the goal is that if people know when they went to sleep last night, which they had to submit the survey, they would have known like what that 3 hour range is, and they could check their social media or their screen report, which they had to submit as well, and they could see like what that 3 hour block was and how they spent it. We have one more quick one. Quick one, sorry. Yes.
So I might wonder about why students had less sleep the night before, or more rested. Was there sleep deprivation when there was more homework to be done? And therefore, the following night, you got more time for social media, or reading, or games. It's driven by the night before.
Yeah, I mean, it's definitely a possibility. I mean, I feel like, anecdotally in my experience, I wouldn't like choose to get like 6 hours of sleep, even if it meant I could get like 10 next night. So I feel like I would rather choose like 8 hours of sleep both nights. But it is entirely possible that people are more.
6 hours if you've got a big assignment that has.
Well, yeah, if you had to, yeah. Well, yes, that's where the majority of the participants did indicate on like most nights that they had something that forced them to stay awake or forced them to wake up early. Etc.
All right, we have come to the end of session 1 of our Wildcat Colloquium. It is now time for the food and the mingling and the chatting with all these amazing scientists and each other. So go enjoy, and we really hope you come back for session 2 starting at 7:45 in this room. To our Zoom participants, go get yourself a snack. Join us at 7:45. Thanks. All right. Welcome back, or welcome to those of you who are joining for the second session tonight. Welcome to the 8th annual Marin Academy Research Collaborative Wildcat Colloquium. I will be doing my spiel at the start again because people may have joined for just the second half. So for those of you that were here the first half, this will sound familiar, but I guarantee you that nothing else you will hear will sound familiar. All right. Thank you all for coming, those of you in person and as well to our Zoom audience. We are so glad that you're here to celebrate the accomplishments of our 8 senior independent STEM research scholars. I'm Amy. I'm the coordinator of the Marin Academy Research Collaborative, or MARC program. The program supports students in developing skills and literacy in scientific research and then applying that knowledge to contribute to real-world research in their STEM area of interest. So they pick the topics that they are working in. And they partner with the broader scientific community with expertise in those chosen areas. So we are in for another exciting round of speakers tonight, hearing about work that students have been doing for the past 2 years, gaining really a level of expertise in these specific areas of their research projects. So it's a 2-year program. They all started as juniors. We have some juniors that are currently in the program here with us. Can you just give a little wave, juniors? Yay. So please come back next year, same time, same place, and we'll be hearing from them about the projects that they will be carrying out over the next year. And I guarantee you they will be on completely different topics than what you're hearing tonight. Okay, many people support students in this process of doing scientific research to ensure that these projects come to fruition. As you saw in the first half, each student will acknowledge specific people that were particularly impactful for their projects. But just in general, I would like to take some time to thank all the people that are involved in supporting these students. So starting with their scientist mentors. Every student here working on their project works really closely with a professional scientist in their field of interest. Those mentors volunteer their time. They're not partnered with the school in any way. They are inspired by these students and decide to work with them as a volunteer. So thank you so much to our mentors. Some are here tonight and we really appreciate you. Also, the family and friends and supporters of our scholars. The journey can be rough at times. There's lots of ups and downs in the research process, and we just appreciate everyone to help support these students in reaching their goals. The community broadly, we really appreciate the support from the MA administration and MA community. MARC is one of MA's signature programs, and we are grateful for the support we get to allow our students to do this cool work. To the MA Science Department, many of whom are here making this event run, and to Ellie, the department chair. And all throughout, these students, all 4 years, have been supported in and out of the classroom by our science faculty. So thank you. Dr. Emily Willingham has been played a major role in these students' work here. She covered my leave while I was out on family leave for several months this year and worked really closely with these students in really critical moments of their project. Story Oates was the MARC coordinator before I came here. She launched the program back when it started 8 years ago, and really laid the foundation for what MARC has become. So thank you. Facilitating student research at this high level in high school requires a lot of support. And I want to extend an invite to this broad community right here. If you have ideas, connections, if you are a scientist, or you can think of other ways to help grow our program so we can continue supporting and empowering these students to contribute to real world scientific discovery, please reach out. You can find my information on the MA website, and I would love to connect. Okay. For the second session tonight, we have another great lineup of speakers sharing really exciting work they've done in these completely different fields. Each student will present for approximately 13 minutes, leaving approximately 2 minutes for questions. If you have burning questions and we don't get to it, please know that you can reach out to these students. Many of them are putting their email addresses and QR codes to find them up here, and they welcome, I will speak on behalf of them, they welcome the dialogue. We don't have a reception afterwards, so you won't get that chance. But please do reach out if you would like. We will try to stick strictly to our timeline with each student starting at their assigned time. And we will be going until approximately 9 o'clock tonight. Restrooms are out the door to the left, and there's an emergency exit here and here where you came in. That's all from the business side of things. We're so happy that you are here. And we will be starting with Drayson Jaffe, who will share. Oh, let me pull up your talk. So we'll be getting started in just a moment. This slide probably wouldn't support your talk very well. Our first speaker of session 2 is Drayson Jaffe, who will be sharing his work, Disposition Scores for Leo Vetter, Fully Automated Vetting for Test Planet Candidates. This is work done in collaboration with Dr. Steve Bryson of NASA.
As Amy said, my work is Disposition Scores for Leo Vetter, Fully Automated Vetting for Test Planet Candidates. And my work is conducted in collaboration with Dr. Steve Bryson of NASA. So, the first exoplanet was discovered in 1992. In 2009, NASA launched the Kepler Space Telescope with the mission to find Earth-like planets, or in other words, to find planets suitable for life as we know it, or aliens. However, as with many really cool things, there's a lot of math and equations behind it. So that's what I've been doing for the last year or two. So I'll break it down step by step. First up is planet candidates. This is an image of the star 2M1207, orbited by the very creatively named exoplanet 2M1207b. And this was the first exoplanet ever directly imaged. And this is a photo from 2010. An exoplanet is a planet which orbits a star other than our sun, or a planet outside of our solar system. And exoplanets are everywhere. We estimate that there are billions in our universe, and naturally, as humans, we want to categorize and catalog every single one. So, but you may as well, a very literal analogy, you may as well try to point out a rock in like a pitch black field in the middle of the night. So what we do instead is we set up a big camera, send it into space, and it looks at the sky, and when it sees something of interest, it logs it as a planet candidate. And this big camera is called TESS, which stands for Transiting Exoplanet Survey Satellite. So it's a satellite up in space, orbiting Earth, and it's surveying patches of sky, and it rotates through them, and it's observing the brightness of all the stars there. And when it sees something of interest, or what it's looking for specifically, is a transit. It's monitoring brightness, and when it sees something that looks like a transit, it notes it as a planet candidate, as an object of interest. So a transit is this here. So we'll give you a second to watch that. Notice how it's a larger percentage of the star is blocked. It's a greater dip. So this left image, that's so there it is. Okay, that left image is called a light curve. Notice how there's a bit of variability with the gray dots, but it averages out to a pretty clean line, and that's expected. There's going to be some variation in flux. Flux and brightness are interchangeable, and when there is a transit, that measured flux drops. Specifically outside of the statistically probable range for the target star, for rising back up when the exoplanet completes the transit, when it finishes passing in front of the star. And this, when Tess sees this, it raises alarms, or rather the opposite, and this event is noted as a planet candidate. So, that's there. We've now covered what is an exoplanet, what is Tess, and how Tess finds exoplanets. So now we have this giant database full of all these possible exoplanets. So Leovetter was created. And it's what it effectively does is distinguishes. It's like looking into a terrarium and trying to distinguish stick bugs from sticks. That's what Leovetter does. So Leovetter was created by Dr. Michelle Kudimoto, and at this current time, Tess has identified thousands of planet candidates, and these are all different sizes of planets, different kinds of planets, all orbiting different kinds of stars, different sizes of stars, different brightness. There's a ton of diversity in data collection. So manually vetting every single one of those is pretty hard. So what we do instead is create an automatic vetter called Leovetter. And it is a public and fully automatic vetting tool, which is capable of efficiently creating catalogs of promising planet candidates. So it picks out those planet candidates that are most promising and turns it into a much smaller and much more manageable database. And the way that it does this is through metric thresholds. Each planet candidate is comprised of numerous metrics, each of which are a numeric value. And what Leovetter does is it sets a threshold that each metric has to meet in order to be considered a viable planet candidate. So there was the issue of manual vetting. Leovetter was created as to be an automatic vetting tool designed specifically for tests, and it identifies promising planet candidates. So talked about planet candidates, we talked about vetting, we talked about Leovetter. Now we're going to dive into the work that I contributed to, the disposition scores for Leovetter. So with this database of promising planet candidates, manual vetting is easier. It's a smaller load to work with, but there's still hundreds of planet candidates and there's no way of differentiating them at a glance. So we introduced the false alarm disposition score. This is a value between 0 and 1 that is calculated for each planet candidate. A score of 1 means that it's far from the threshold, and we're very confident in it being a planet candidate or being a promising exoplanet. And a lower score could be a false alarm, and a really low score raises serious concerns. So this is not a probability. It's very important to know. A score of 1 does not mean it is 100% a planet. A score of 0.4 does not mean it's a 40% chance to be a planet. This graph has 172 points, and each point is a planet candidate that Leovetter classified as promising. The axes are in log scale. It's period in Earth years, which is the time it takes for an object or an exoplanet to orbit around its star. For example, Earth has a period of 1. And signal to noise ratio, or SNR. The higher value means there's a stronger signal. The lower value means it's a weaker signal and greater noise. And the column is the calculated disposition score, indicated by the color of the point. So yellow means more confidence, blue and purple means less confidence. And notice how as the signal to noise ratio shrinks, as the period grows, you have greater uncertainty in general, which is what we would expect to see. So in order to calculate the score, we use Python with Jupyter We create first step, we created simulated light curves with diverse period and SNR values. So we then had over 60,000 essentially fake transits. And using these, we put them all in a 30 by 30 grid. And this gives us a solid idea of how a transit should or could look at different period and SNR values. This is useful for determining whether real data is a transit or not, and it allows us to see how a real planet would look in different conditions. Each injected transit, each of these fake transits, are comprised of the same metrics that make up real planet candidates. So we then took a graph with period and SNR on the axes, divided it up into a 30 by 30 grid, and for each individual metric, we measured the uncertainty. The graph on the right is an example of this. The higher values on the bottom, these warmer colors indicate greater uncertainty, and the cooler values mean that we're more certain in the values. There's less variation. So then for each metric, we fit a polynomial curve, which describes the variability. So we take a graph like this, and you make an equation that describes how it works, like what it looks like. and how it varies across the bins and works at different periods in SNRs. So for example, this is V shape. And what it's doing is it's differentiating, it's a numeric value that tells you how close it looks to this as opposed to that. So it's identifying, so this is what an eclipsing binary would look like. It's more of a V shape. And that's when you have two stars going in front of each other. So it's a star blocking another star versus a exoplanet blocking a star, which gives you more of that U shape. So what this is it's differentiating between those two. So now for each metric, we have an equation which describes how much variability we would expect to find. So now it's time to calculate the distribution score. We created a program which randomly tweaks the metric thresholds used by Leovetter based on these equations. Then we ran this program 1,000 times for every single planet candidate. We counted how many times it passed these modified thresholds. And we then divided the total number of passes by the total number of runs, obtaining this graph. So these are the results. A low SNR, high period means more uncertainty, whereas a very strong signal and a lower period means that we're a lot more confident in the planet candidate. So to summarize, the disposition score is the fraction of runs which pass the Leovetter's thresholds, which were adjusted for each independent run based on the expected variability that we found. And this reveals which planet candidates are very promising and which ones are barely meeting the necessary thresholds. And it helps us evaluate how likely a planet candidate is to truly be a planet. So does it work? We have the results, but does it even work? This is example A, example B. Example A received a score of 1.0. Example B got a score of 0.766. So example A, you can see there's very clearly a dip. Looks pretty U-shaped. We're very confident that that is a planet or an exoplanet. This one though got a much lower score, 0.766. And there is a dip. There is a dip that was identified, but it's much shallower. This is about a 6% transit. This is about a 0.1% transit, which is still possible, but it's far, we can't be as confident in it. And notice how the gray dots up here, it dips way below that statistically probable range. But here it's very possible that it's within a statistically probable range. So it could just be pure randomness, pure chance that happens. So this is the current state of it. This paper was actually just submitted a few hours ago. Leovetter, fully automated flux of pixel level vetting of test planet candidates to support occurrence rates. This is the paper for Leovetter. Leovetter is actually, it was just published a few hours ago, and it's actually a huge project, which is highly anticipated in the field. And my work on the disposition score will be included as a section on the paper. So my acknowledgements, thank you to Dr. Steve Bryson, my mentor. Thank you to Dr. Michelle Kunimoto. Thank you to Amy. Thank you to Emily. And thank you to my MARC peers. Questions? This is the QR code you can scan, which directs you to a Google form to ask questions and then get forwarded to my email if I don't get to. The only posting binaries, those are fairly common.
Go
More,
back to that.
yeah.
Ah.
What do you think? That's a binary star system. That's when two stars, they're, I guess, orbiting each other. I don't know if that's the right phrase, but they pass in front of each other. Like an example of this is Polaris, the North Star. It's pretty cool. It's more common than you think, is my answer.
Candidates for that.
I don't have an exact number for you. Many. I mean, it's a very easy thing to see this and consider it a possible planet candidate. When it's obvious, it's obvious. A lot of situations, it's not as obvious as this, but it is an issue, and this is what Leovetter and the distribution scores address.
So what does this data lead to once you identify candidate less likely, more likely? What do you do with that information? Is it limited resources where you point telescopes? So this kind of gives you clues where you should aim them next, or?
This is a tool which helps us. So the ultimate goal is to find exoplanets, find confirmed exoplanets, know which of the things that we're looking at are what we want. So the disposition score is a tool which we use to direct our attention to the less the planet candidates that we have less confidence in. To direct so that we can then manually vet those planet candidates that are more on the fringe, which aids in the process, speeds it up, so that we're not looking at the obvious ones or the ones that we have no chance in.
And a question from Tenzing in the chat. How close is the closest high probability candidate?
Those are the closest high probability, like closest to Earth, I'm assuming. I don't know. I actually don't know. They're everywhere. My assumption would be that they're fairly evenly spaced out. I mean, the closest one is probably in the closest galaxy, but maybe Andromeda. I actually don't know. But that's a good question.
All right, thank you, Dave. Thank you so much, Drayson. Moving on, we will hear next from Tyler Hackman, who will be sharing his work assessing the progression of Alzheimer's disease in mice using computer vision and machine learning. This was work done in collaboration with Dr. Stephanie Miller and Katie Lee from the Gladstone Institute of Neurological Disease.
Thank you, Amy, and thank you everyone for coming out tonight. So as Amy said, my project is on assessing the progression of Alzheimer's disease in mice using computer vision and machine learning. And I collaborated with Dr. Stephanie Miller and Katie Lee from the PALIP lab, which is part of the Gladstone Institute of Neurological Disease at UCSF. So just starting off, why is Alzheimer's so important to research right now? So first is the most common form of dementia in the world, and in the US alone, around 7 million people live with Alzheimer's. And by the way, I'm going to refer to Alzheimer's as AD in this presentation, so just know that. However, in 25 years, in 2050, cases are projected to nearly double to 13 million. And also the health costs related to aiding these people who live with dementia is expected to reach 1 trillion. So there are pretty significant aspects and many factors of life. So how does Alzheimer's occur and what is Alzheimer's? So when we talk about Alzheimer's, there are two main categories: familial Alzheimer's or early onset and sporadic Alzheimer's. So familial Alzheimer's is really rooted in genetic mutations, while sporadic Alzheimer's is more kind of related to lifestyle or just general aging. So kind of like Jasmine was talking about in her presentation. And so what is really causing neurodegeneration in the brain? So the most commonly accepted hypothesis for a long time now is that a buildup of a protein called amyloid beta forms toxic plaques in the brain that lead to cell death and neuronal dysfunction. So we look at a cross-section of a healthy versus sick mouse hippocampus. These little spots here are that buildup of that toxic protein. And that protein, amyloid beta, is derived from a larger protein called amyloid precursor protein, or APP, which is found in the cell membrane of neurons and many other cells in the brain. And like any other protein, when a cell is done with APP, enzymes will come and slice up that protein into soluble pieces that can be cleared from the cell and cleared from the brain. However, certain genetic mutations will change the region of the protein that is sliced by these enzymes. And some of these pieces end up being larger and chemically stickier and also insoluble. So they aren't able to be cleared from the brain, so they aggregate and end up forming these toxic plaques. And because we know that Alzheimer's can be rooted in genetics, we often turn to mice to study the disease because we can genetically engineer them. So we can give them specific mutations that end up mimicking human-like Alzheimer's. Also, we share, as mammals, we share a lot of biological mechanisms with mice. So, they're kind of a good species to make comparisons to humans. And also because Alzheimer's is related with aging and mice have a very short life cycle, they're very effective for studying the disease. However, mice do not get Alzheimer's naturally, which is a limitation. So, we have to rely on genetic engineering to mimic human Alzheimer's. And also we can assess their cognition in the same way as a human. We can't just ask a mouse like, how are you feeling today? Like we could a human. And thus, we have a lot of methods to sort of quantify behavior to study mouse cognition. And so some common tests that you may have heard of before, one of the most prominent examples is a Morse water maze test. And essentially how this works is that we assess how long a mouse takes to get to a platform within sort of a container of water. And we see that over time, healthy mice will learn to get to the platform faster, while sick mice who aren't able to, effectively form memories or have memory loss, keep taking a long time to get to the platform. Similarly, another way that we measure learning or memory is in the novel object recognition test. And so we know that mice prefer novelty. And so we first habituate them in a chamber with two of the same objects and then remove them from that chamber. And when we put them back in, there's a new object. And essentially we measure how much time the mouse spends exploring each object. And we see that in healthy mice, they'll spend more time exploring the novel object because they know they've already seen the old one. Whereas in sick mice, they spend around this same amount of time at both. So we have a lot of other tests that also that we also use to study memory and learning, but really these tests are somewhat limited in how they evaluate the full scope of behavior because they're limited to specific cognitive domains. And so with advances in machine learning, we're actually in the process of developing new methods to more thoroughly and holistically study behavior. So what might be the benefits of using a machine learning approach? Well, first, as I said, machine learning kind of enables a more holistic and even unbiased analysis of animal behavior because it's not limited to specific cognitive domains. Also within machine learning, we have both supervised and unsupervised learning. So what this means is in supervised learning, we are providing a model with a labeled data set. So essentially we're giving a model a pattern to learn, and then it learns to replicate that pattern on unlabeled data. However, in an unsupervised learning model, we simply give a model a bunch of data and ask it to tell us what it finds. So in that case, it's identifying its own patterns and then feeding that back to us. Also, another great advantage of using machine learning is that most machine learning tools are open source, which means that a lot of research is easily replicable, which is very important. So I'm going to dive into the machine learning pipeline that I use with my mentors. So first, we record mice in an open arena test. And so rather than performing a specific task that's going to measure memory as a single number, these mice are basically able to exist as they would, and they're able to behave as they would without any influence. Then we use our first machine learning tool called Deep Wildcat to track 11 body parts throughout the whole video. So you can see a little labeled video of this mouse walking around with 11 body parts labeled. From Deep Wildcat, we basically get out a bunch of XY data in the form of these humongous CSV files. And so if we sort of visualize what these files might look like, we see that we're really just tracking where each body part is in the arena over time. And now that we know where each body part is in the arena over time, we use our second machine learning model, which is called VAME, which stands for Variational Animal Motion Embedding. And essentially what VAME does is it uses a k-means clustering algorithm, so that's the machine learning part, to look in all of that XY data and look for patterns of repeated behaviors, which we call motifs. So if we look at this figure over here, we see that VAME identified walking as, the right paw moves in this way, while the left paw moves in that way, while the nose is doing this. And from that, we actually see, if you look at this little video here, we see that VAME very effectively is able to categorize behavior and kind of spontaneous changes in behavior. So we see this mouse is, walking now, and then it's going to transition to, an exploring behavior. And so you can kind of see how this is more holistically capturing behavior rather than just a measurement of memory. Also, by the way, the K in k-means clustering, the K stands for, or the K represents the number of clusters we want, the number of motifs. So just keep that in mind. Normally, we identify 30. Then our final step is to actually compare these motifs and compare the expression of these motifs. So some common measurements we make are the time that the mice spend in each motif, also the speed that they're performing these motifs. So if it's a sick mouse is performing a running motif faster than a healthy mouse. That's kind of a sign of hyperactivity. And then something that we also can measure is the probability of transitioning into a similar style of motif or a similar behavior. And essentially, what that helps us do is evaluate overall organization of behavior. So, are these mice spontaneously going into very different behaviors, or are they kind of staying consistent in their behaviors? And you don't need to understand these graphs, but these are sort of just some usual measurements we make. So just to recap really quick, we basically go from mice existing as they would normally in an arena, and then we're able to, using VAME and Deep Lab Cut, we're able to identify what behaviors they're using. So this method was published earlier this year by my mentors. So this is a paper by my mentors. And one prominent result they found is that they demonstrated that spontaneous machine learning behavioral changes are detectable in between when disease pathology starts, so when plaques start to form, and before obvious signs of cognitive impairment like memory loss, as we can kind of see in this figure here. And so what that means is that there is a clear window in which therapies are most likely to be effective in making it so that people don't actually go on to develop dementia with cognitive impairment. So kind of this middle region is the ideal timing for therapeutic interventions. And this also tells us that if we can now measure very early signs of Alzheimer's using machine learning, we can better make medicines for early stages. And thus, I noticed from this that it is very important for us to understand how these spontaneous behavioral changes occur over time. And so when I was brainstorming, how can I build on this method? I came up with the idea of investigating how VAME actually captures disease progression over time. So basically, my project, I had sick mice and healthy mice recorded at 2 time points. They're actually recorded at 3, but I'm only looking at the second and third. And we see that there's this kind of 9-month span, so a lot of time for disease progression. So some results. So first, we're going to be looking at motif usage. So I know this looks like a lot, but basically, these graphs are time in motif over a 20-minute span. And so there are 30 little graphs for 30 little different behaviors. And the blue line is going to be the earlier time point, and the green line is going to be the later time point. And also, these are all healthy mice. So to sort of set a baseline of how behavior changes in healthy mice over time, we can see that in 8 out of the 30 motifs or the different behaviors, we see statistical changes over time. However, we also are going to look at these results in our sick mice. So now our black line is the earlier time point, and the red line is our later time point. And so if these mice, if they're healthy, we would expect to see 8 out of 30 motifs change. But in reality, we see 24 out of 30 motifs changing. So that's a 300% increase from the healthy mice. And so this is telling us that there are obvious disease-related changes that this machine learning program is picking up on. So I kind of just wanted to zoom in because I know that this looks like a lot. So let's just look at motif 18, for example. So we see that in the healthy mice, at both time points, the mice are spending around 2 to 5 seconds in this behavior. However, and we don't really see a significant difference between them. However, in the sick mice, we see that at the first time point, they're spending around 5 to 10 seconds in that behavior, but then at the second time point, the sick mice are almost double that. So we see a significant change in the behavior, especially compared to the healthy mice. So now if we look at a video of what this behavior actually looks like, so this is every instance of motif 18 from one video, we see that sort of like this running or exploring behavior. And it's also generally around the outside of the arena. And so what this tells us is this might be a sign of AD-induced anxiety or hyperactivity. Also, if we look at the speed in which the mice perform motif 18, we see that at this first time point, the healthy group and the sick group perform it at roughly the same speed. However, at the later time point, the sick mice are actually performing it faster. And so that's another sign that maybe these mice are showing signs of Alzheimer's induced hyperactivity. And so You can imagine how many results I would have if we have to do this for every motif. So these results are definitely to be continued. However, based on what I have now, we can make some conclusions. First, to answer my question, VAME is clearly reflecting a lot of Alzheimer's-induced behavioral changes over time. And what that tells us is that we can use this information to inform timing of therapeutic interventions in conjunction with that paper that I was talking about earlier that my mentors just published. Also, in general, because we're trying to make this one-to-one comparison of behavior to cognition or well-being in mice, these results will also just develop or help us develop a more robust understanding of what kinds of behaviors are impacted by Alzheimer's. So that's my presentation. I wanted to give a huge thank you to Dr. Stephanie Miller, Katie Lee, Dakota, and the entire Palop lab, Dr. Palop, Amy Strauss, Dr. Emily Willingham, the MA Tech team, and to my MARC class of 2025. Have time for one or maybe two. I don't want to call him my dad, but yeah.
Looked like the mouse was running around the walls of its little bucket.
Yeah.
That's really normal.
What?
It looks like the mouse is running on the walls of its.
Oh, on the walls? Right. So okay.
That's really accurate.
So what the reason it looks like that is this is a if we have a circular arena, this is a view from below. So I think that might just be the perspective. However, if we look at some of our example motifs, sorry, we also see that rearing is one of them. So kind of when it's up on its hind legs. So one behavior we do actually capture is when the mouse is up on the wall. So yeah, that is definitely. I mean, oh, actually, look, it's rearing.
One quick.
Okay.
How many mice need to be used to defining the motif by machine learning?
That's a good question. So my model was trained on 37 mice, and it was a well-trained model. So really not that many. However, obviously, the more data you have, the more reliable and consistent your model will be. Thank you.
Okay, next up we have Amrit Chadha, who's going to be sharing his work Mapping the Market, a structural analysis of India's carbon offset ecosystem and its global buyers. This was work done in collaboration with Dr. Mook Bangalore of Penn State University. Come on up.
Thank you all. Thank you all. Please don't fall asleep. That's all I ask. Hello, everyone. I'm Amrik, and I'm going to take you into the world that most people really just have not seen yet. The global market for carbon offsets and India's surprising role at the center of it. So you've probably heard about companies planting trees or investing in clean energy to offset their emissions. What if I told you that most of these projects are happening in places like India, and they're being paid for by countries halfway across the world? With the guidance of my mentors, Dr. Bangalore, Margot Alfair, and Dr. Sonali McDermott, I built a data set, analyzed thousands of transactions, and tried to figure out who's buying, who's selling, and whether this whole system actually works the way it's supposed to. So let's dive in. Why does this matter? Why should anyone care about carbon offset markets or India's role? The first reason is simple. Climate change is global, and it's the biggest problem our generation will inherit. But while we've heard about reducing emissions, there's a whole side of the system that's about moving emissions around through these carbon markets. These markets let companies outsource their pollution cleanup. Instead of cutting emissions themselves, they pay someone else to do it. And often that someone else is a project in a country like India. India has become a global carbon credit supplier, but the market is extremely messy. A lot of buyers aren't transparent. We don't know who they are, what kind of projects they fund, or if those projects are even working. And that raises bigger questions. Is this system actually helping the climate, or is it just helping corporations look better? So before we go any deeper, let's just break down what a carbon offset actually is. Imagine this: you run a factory or an airline, and you can't fully eliminate your carbon emissions. So instead, you pay someone else to do something that helps the environment, like plant trees, install solar panels, or capture methane from waste. That's a carbon offset. It's like saying, I'll keep polluting here, but I'll pay for someone else to clean it up there. Offsets are meant to cancel out your emissions by reducing or removing CO2 somewhere else. It sounds good in theory, right? But the system depends on whether those projects are real, permanent, and actually helping. And that's where it gets tricky. Once I understood how carbon offsets work, I had some big questions. And honestly, they're questions that not enough people are asking. First, who's actually participating in these carbon markets? Are these mostly big corporations, nonprofits, governments? And second, what kind of projects are getting supported? Is it just renewable energy or investing in transportation, waste, agriculture? Third, where is the money coming from? Which countries are buying these credits, and are they buying it responsibly? Finally, is the whole system fair? If countries like India are doing the heavy lifting, building the projects, hosting the risks, but rich countries are buying the credits and claiming the glory, is that a just system? These are the questions I used to guide my research. And once I had my questions, I needed data. And this is where things just kind of got a little real for me. I pulled from three main sources: the Berkeley Carbon Trading Database, Carbon Plan, and Offset Map. Together, they gave me over 1,200 carbon offsets from India, plus tens of thousands of records about which entities bought the credits from them. But here's the thing: the data was very incomplete. Some entries were missing buyer names, some had no country, and some listed whole spreadsheets as just unknown. So I spent weeks basically doing detective work. I added missing info, finding buyer countries, checking corporate websites and LinkedIn, and tagging companies by ownership type and industry. No one had looked at the market as a full ecosystem before, but by cleaning it up, I was able to finally start seeing structure underneath all this noise. This is before the noise, after noise. And as you can see, lots of projects. Basically, this times 12 is my database. And I'm just going to handpick one of these projects, okay? The Breathing Space Improved Cooking Stoves Program, India, all that. This project was run by EnviroFit International, and it was just distributed efficient cook stoves to households in India. It was certified by Gold Standard, tagged as energy efficiency, and it issued and retired 72,073 credits during its 10-year crediting period. On paper, that looks like a great project. It cuts emissions, improves health, and supports sustainability goals. But even here, it's hard to track who actually bought the credits, what price was paid, and whether any of that benefit reached the local communities. And that's the case for 100 projects in the system. This slide shows what one good project looked like, but how little visibility we have. And I could just do this all day. I mean, it's just non-disclosed like everywhere, right? But then we needed tools to kind of clean this up, okay? We have this non-disclosure. We have to break down all this in a way that can reveal something new. I use tools like Python for sorting and grouping, Data Wrapper to make a map, and Excel for checking for weird inconsistencies, like if the same company appeared under different names, or if the same project was listed with different descriptions. And I grouped everything into four main categories. Ownership type. Are these buyers private companies, nonprofits, individuals, or just completely unknown? Then there's a project type. Are they mostly funding renewable energy or other sectors like transportation or waste management? And then the industry sector. What industries are buying these? Okay, are they tech firms, banks, construction companies? And finally, buyer country. What nations are purchasing these offsets? So this helped me move from just a list of names to a map of relationships. And that's what led to the next four findings. So here's what I looked at: what types of entities are buying the carbon offsets from India. More than half the buyers, which is 50.3%, were listed as either unknown or non-disclosed. That means we don't know what kind of organization they are, who they work for, or what industry they are in. Among the ones we could identify, private companies made up around 37%, individuals were just under 10%, and nonprofits were barely 3.5%. That's a problem, because we don't know who's using these offsets. How do we hold them accountable? So next, I looked at what industries these buyers actually come from, okay? The most common, where we could identify it, was energies and utilities, which just makes sense since a lot of these companies are trying to offset emissions from electricity, oil, or infrastructure. But the real story, nearly 40% of these entries fell under other or unknown. That means we don't know what kind of business businesses are using these carbon credits. The few industries that do show up, like transportation, professional services, and environmental services, suggest that it's not just energy giants involved, right? It's also firms trying to meet like different goals or appear green. Honestly, the scale of other and unknown is just kind of wild to me, right? We have a lot of blind spots. And there's a few reasons why so many buyers fall into this other unknown category. Some are brokers or shell companies, and some are just listed by name with no public information attached. And some, let's be honest, may not want to be easily found. The voluntary carbon market has really low transparency rules, and that makes it easy for companies to stay vague, especially if they're using offsets for PR or to dodge regulation. Either way, there's a huge gray zone, which makes it hard to understand who's really behind the market. So who's actually buying these carbon credits? This map shows the countries with the most carbon credit retirements from Indian projects. 4 countries dominate: Australia, the UK, Germany, and the US. Together, they account for almost 60% of all the purchases. Interestingly, Australia tops the list, even ahead of the US. That could be because of stricter emission rules there, or because Australia has a strong brokerage network that trades on behalf of others. Another surprise is Singapore. Even though it's tiny, it has over 800 entries. And that's likely because it's becoming a carbon finance hub in the Asia Pacific. Meanwhile, countries like Japan and Canada, who are seen as climate leaders, barely show up. And yes, India does show up too, because there are a few domestic companies that are buying credits from within the country. But it's a tiny share compared to its global buyers. So you kind of have this dynamic, the global south builds the projects and then the global north gets the credit, literally. Let's talk about what kind of projects are actually being funded. This chart shows the number of entities tied to each project type. And as you can see, it's not even close. Renewable energy absolutely dominates with over 28,000 buyers. Meanwhile, sectors like transportation, energy demand, and waste management are ignored. And that's a missed opportunity. These sectors have a lot of potential for carbon savings, stronger co-benefits for local communities, like reducing air pollution or improving clean access to tech, but they're just not getting the same love. So why does this matter? Why care about buying carbon credits or who's buying them? This isn't just like a data story, okay? It's about power, you have accountability, and you get to see who shapes climate solutions. Let's be real, the data is a mess. I had to pull from scattered registries, sort through mislabeled entries, and manually research buyers. And I'm a high schooler, and that took me 8 months. That alone tells you something. This system is opaque by design. Once I made sense of it, patterns started to emerge. Wealthy countries like Australia, the UK, the US are buying most of these credits, and countries like India are hosting the projects, but rarely get the credit or the control. So India absorbs this climate vulnerability. If a forest burns or a cook stove project collapses, the emissions still count, but the buyer keeps the credit. If the offsets are oversold or invalid, it's India's credibility on the global stage that takes the hit. And here's the twist. Even though carbon offsets are supposed to be green, many buyers stay anonymous. Why? Maybe they don't want scrutiny over what they're buying, how much they're still polluting, or whether they're double counting credits. I even saw some projects with multiple buyers, which in a poorly regulated market can mean overselling, double counting, or funding something that would have happened anyways. That's called a lack of additionality, and it undermines the whole idea of offsets. So this isn't just a climate market, it turns into a power market. And if we want real climate justice, we have to ask who benefits, who's left out, and who's being asked to trust a system they don't control. So no study is perfect, and in this case, the limitations are kind of part of the point. First, I only studied the voluntary carbon market, not India's new compliance market. That side is still developing and harder to access. Second, the data gaps were huge. More than half the entries lacked key information, like who the buyer was, what industry they're in, or even if they were a real company. Many were shell firms or vague intermediaries. That's not just my limitation, it's a market design issue. And finally, the study focused on structure, not outcomes. I didn't analyze whether projects were effective, additional, or delivered real benefits to communities. That's critical work for future research. So if this study is a map, it shows the outline, but not the terrain. Still, the fact that a high schooler had to build the map from scratch says a lot. So what do we do with all this? Well, I could tell you we need a UN body, like the UNFCCC, or to regulate buyers, or that we need more diverse projects, or a greater community inclusion. But that's not why I started this project. I started because I suspected something bigger, that carbon offsets are not what they claim to be. 2 years ago, I was sitting in a summer course on the philosophy of economics at USC. The topic that day was carbon credits. The idea sounded perfect to me. Okay, pay $40 to raise the emissions from your $400 flight. It was elegant, but maybe too elegant. That day sparked something. I spent the next 2 years researching the $480 billion global carbon offset industry. And I built a data set from scratch. I dug into thousands of transactions and I found out what I confirmed from my early doubt. The system is opaque. Over half the buyers are anonymous. Credits are sometimes sold to multiple entities. Some projects likely would have happened anyway. The Global South hosts the projects, the Global North claims the benefits. In other words, this isn't a functioning carbon market. And if our plan is to save the planet, we're in trouble. So here's what I think we should do instead, based off of everything I've seen. First, the carbon credits should let companies buy the image responsibilities. And it's sad right now because they get to buy that image and they get tax deductions for it. That's backwards. Polluters should pay for real infrastructure, things like wildfire defense, flood protection, or clean water systems. We need to electrify everything. Trucks, freight, boats, buildings, anything that runs on fossil fuels should be shifted to electricity. Offsets can't hide the fact that emissions are still happening. This is how we cut them from the source. Next, we need to make our systems stronger. Our power grids, roads, water systems weren't built for the kind of climate we now live in. We need to invest in resilience, especially in vulnerable countries, not just in the ability to offset risk elsewhere. And fourth, I think we should treat climate like a security issue. Imagine if we mobilize the same way we do for national defense. Climate threats are already destabilizing regions. Let's take this seriously without waiting for consensus or delay. Because here's the truth. Carbon offsets were supposed to be a bridge, but now we've turned them into a destination. I want to thank my mentors for supporting me throughout this project, and a special thank you to John Haidman, Dr. Emily Willingham, Amy, and my MARC class. I still don't know if carbon offsetting is a scam, but to me, I think so. It's for you to wonder. Thank you very much. You can take one question. Yes.
So, in your example, then you find where United Airlines, American Airlines, Singapore Air are buying.
Yeah.
Where they are.
I can actually look individual to a single project and find entities like United or something like that. Or I saw like Man U was buying carbon credits. And I could see, I wouldn't be able to go directly to that project. I wouldn't be able to see if it was functioning the way it would. But the scale of the amount of carbon credits where entities weren't disclosing who they are was at mass. Like when I went back into those slides, I just cherry picked one of them. And I only showed like 6 slides of the non-disclosure, but there were like 38 just for that one project. So there's a huge scale of just non-disclosure around all projects. And that's just like really worrying because some countries or companies just aren't disclosing who they are, what they are, or what project they're buying. Is that all?
So I have a question. Is it possible that the non-disclosure is because they're worried that people like Trump come in and then say we're against ESG, and therefore we don't want our name out there, even if we do care about the planet?
I know it's shifting. I don't know because some of these projects date back to like 2012. So maybe they're not disclosing like all the way back then. But I do see like how maybe there's a hesitation for the carbon market now and maybe less disclosure now. But I can still see the same trends like dating like 10 years ago.
Thank you, Emma. Thank you, Emery. And our final speaker of the night is Eloise Sant. She'll be sharing her work, Epigenetic Inhibition of the ERBB2 oncogene to treat HER2-positive breast cancer, work done in collaboration with Dr. Chris Benz and Dr. Gary Scott of the Buck Institute for Research on Aging.
All right. Thank you so much, Amy, for the introduction, and congratulations on making it to the last presentation of the night. I will try to be as engaging as possible. So today, my research focuses on the epigenetic inhibition of the ERBB2 oncogene to treat HER2-positive breast cancer. I know that probably sounds like a lot of crazy words right now, but I promise that I will definitely explain them throughout the presentation. So just to begin with some background, about 1 in every 8 women in the United States will develop breast cancer at some point throughout their lifetime. And sadly, this makes breast cancer the most common malignancy in women worldwide. And as aging increases, so does the risk of breast cancer. There are 3 different key molecular breast cancer subtypes that I'll talk about today. So the first type is estrogen receptor or progesterone receptor positive breast cancers. These make up about 70 to 80% of overall cases, so the majority of cases that we see today. The second type is emphoblastic oncogene B, or ERBB2 positive breast cancers, which make up about 15 to 20% of overall cases and are the primary focus of my research. And then the third type is triple negative breast cancers, which means they are neither estrogen receptor, progesterone receptor, or ERBB2 positive. So the first key question that we have to answer is, so what actually causes ERBB2 positive breast cancer? ERBB2 positive breast cancer is caused by the amplification of the ERBB2 oncogene. Oncogenes are defined as genes that can transform normal cells, which you can see, which you should be able to see on the left, and then they transform them into tumor cells, which you can see on the right. So the normal cell in this scenario has one ERBB2 receptor, which is just simply a protein on the cell membrane. And then the tumor cell, on the other hand, has many genomically amplified copies of that same ERBB2 receptor. So what are the different treatment options available for this type of breast cancer today? So current FDA-approved ERBB2 breast cancer therapies include anti-ERBB2 monoclonal antibodies and small molecule ERBB2 kinase inhibiting drugs. So I don't want to get caught up in how these molecular mechanisms differ, but what I do want to point out is that even when they are combined with taxane-based chemotherapy approaches, they often lead to treatment resistance. And this is primarily because they all target the ERBB2 receptor on the cell membrane directly. So this clinical resistance really demonstrates the need for alternative therapies. And one option that is currently being undertaken in the Benz lab is to inhibit the ERBB2 protein expression pathway much earlier on. So this can be done by epigenetically inhibiting the ERBB2 mRNA within the nucleus, which you can see on the screen. So epigenetic inhibition essentially means that we are modifying the gene expression rather than actually altering the underlying DNA sequence itself. So this novel treatment approach is called nuclear ERBB2 mRNA decay. And for some additional context, mRNA, or messenger ribonucleic acid, is a single-stranded molecule of RNA that corresponds to the DNA sequence. And this is ultimately read by ribosomes when synthesizing proteins. So by degrading the ERBB2 mRNA within the nucleus, we first block transcription, which therefore blocks translation, and ultimately the creation of the ERBB2 proteins that we see causing this type of breast cancer. So the next big question is, how can we actually achieve ERBB2 mRNA decay? So the proteins P300 and CBP are both transcriptional regulators of nuclear ERBB2 mRNA. And transcriptional regulators are essentially just proteins which are controlling the rate of transcription, which is when DNA is copied into RNA. So therefore, by inhibiting specific domains of these two proteins, we can actually achieve nuclear ERBB2 mRNA decay. Protein domains are regions of a protein polypeptide chain that are self-stabilizing, which means that they fold independently from the rest of the protein. So my research today focuses on 2 different novel drug candidates that both inhibit slightly different domains of this same protein complex. So the first novel drug candidate is NEO2734, which is a bromodomain inhibitor of these proteins. And then the second novel drug candidate is A485, which is a histone acetyltransferase or HAT domain inhibitor of these proteins. So I know this sounds confusing right now, but the main takeaway that I want you to get from this slide is the fact that NEO2734 and A485 are both novel drug candidates which inhibit slightly different domains of the same proteins, which we know regulate nuclear ERBB2 mRNA. So my research question then becomes, how are we going to test the efficacy of these 2 novel drug candidates in inducing nuclear ERBB2 mRNA decay and ultimately treating ERBB2 positive breast cancer? So this is where my methods come in.
For this study, we used a mouse xenograft model, so 7 to 8 week old immunodeficient female skid mice were first implanted with estrogen pellets to stabilize their levels. And then exactly 48 hours later, 10 million human breast cancer cells were implanted into the mammary fat pads of each mice. The mammary fat pad is essentially like the mouse equivalent of human breast tissue, which means that our results will be directly relevant to human application. So there were 4 different experimental groups, and each group was treated with its respective drug for 15 days. So for context, a vehicle treatment refers to an inert substance which is used to deliver a drug to its intended site. It's often used as a control in experiments to ensure that the observed effects that we're seeing are actually due to the drug or the treatment itself and not due to the vehicle. So that being said, mice from group 1 were treated with the vehicle, which essentially acted as our control group for this experiment. And then mice from group 2 were treated with the first therapeutic drug candidate. Mice from group 3 were treated with the second therapeutic drug candidate. And then mice from group 4 were treated with a combined dual treatment of both drugs. So after the final drug treatment on day 15 of this study, all of the mice were sacrificed, their tumors were excised, and they were immediately snap frozen by Murigenics, who's the external vendor that was doing all of this in vivo work with the mice. And that's when our research really began in the Benz lab. So here you can see, here are some pictures from my time at the Benz lab over this past summer, where I spent 2 months working as a full-time research intern. And as you can see, the tumors were stored in a negative 80 degrees Celsius freezer at the Buck Institute, which is on the left. And then once we retrieved the tumors from the freezer, the first step was to actually grind them up. And to do this, we used liquid nitrogen, a mortar, and a pestle. You can see an example of the huge liquid nitrogen containers that we would get it from when we were at the Buck Institute. And then this process ultimately created protein lysates, which are fluids that contain proteins released from cells once their membranes are broken down. So we then analyzed those protein lysates via a very common laboratory technique, which is called Western blotting. On screen here is me loading a gel to begin a Western blot, and then you can also see the gel electrophoresis process occurring in the middle. And then finally, the dark room where we actually imaged our Western blots. So for some additional context about Western blotting as a technique, I thought the example image on the right would be helpful. So the bands on a Western blot measure the protein levels of a targeted protein or gene. When there's more pigmentation, which means the bands are darker, there's greater gene expression. And when there's less pigmentation, which means the bands are lighter, there's less gene expression. So originally, we were planning to measure the ERV2 protein levels of each tumor sample to determine if they had decreased with either individual or combined drug treatments. However, these results were extremely unreliable, and they were very unreplicable between experimental groups. So for this reason, we had to pivot. And we instead ended up measuring the histone 3 lysine 27 or H3K27 acetylation levels of each tumor sample. So you're probably wondering, what on earth is that? Because that's what I was wondering at first. So acetylation is when an acetyl group is added to another molecule, which is oftentimes a protein. And in this case, the H3K27 acetylation levels represent the histone acetyltransferase or hat domain function of the P300 and CVP proteins, which we know from earlier in my presentation regulate nuclear ERB2 mRNA. So therefore, if the H3K27 acetylation levels decrease in comparison to those of the housekeeping gene, which is histone 3 or H3, then we'll know that the drug treatments are working. So again, I know that was probably a lot to take in, but the main takeaway here is that if the H3K27 acetylation levels decrease, the drugs are working. So that's what we're hoping to see. And now the big question is, so what do we actually find? So this first Western blot that you can see here is a comparison between the vehicle-treated tumors, which essentially acted as our control, versus the A485 treated tumors, which was our first therapeutic drug candidate. So as you can see, the first 4 lanes here represent the vehicle-treated protein lysates, and then the next 5 lanes represent the A485 treated protein lysates. The first row represents the histone 3 lysine 27 acetylation levels of each tumor sample, and then the second row represents the histone 3 expression levels of each tumor. Remember that histone 3 is our housekeeping gene, so this means that it is always produced at a relatively constant rate, and it should not be affected by any of the treatment categories, and essentially kind of acts as an internal control. So the final row, the third row, which is arguably the most confusing, represents the histone 3 lysine 27 acetylation divided by histone 3 band intensity ratios of each tumor sample. We also plotted these graphically for easier visualization, so that's what I'll kind of be focusing more on for my results. Just to note, from this point on, I'll be referring to these numeric values as the ratios because histone 3 lysine 27 acetylation divided by histone 3 band intensity ratio takes kind of long to say. So this is a two-tailed t-test, which shows the numerical ratios that we just saw in the Western blot. So it's representing the exact same data. The x-axis that you see here represents the experimental group, and the y-axis represents the ratios. The dots that you can see on screen that are colored differently represent the ratios for each specific tumor sample that we tested. And then the stars that you see on all of these graphs that I'll show ahead represent the p-value, which is the probability value, and essentially represents how statistically significant or how statistically different two experimental groups are from each other. So if a p-value is less than 0.05, that means there are significant differences between groups. And as the p-value gets smaller and smaller, that means there are greater significant differences. So on this graph, you can see 2 stars, which means that the p-value is less than 0.01. And this means that there are statistical significant differences between the ratios of vehicle-treated versus A45 treated tumors. So the key takeaway here is that the A45 drug, which is our first therapeutic candidate, is very effectively inhibiting the P300 and CBP hat domain, which overall, just in simple terms, is a very positive result. So this next Western blot has all of the same rows as the previous one, but the main difference is that the vehicle-treated tumors are now being compared to the NEO2734 treated tumors, which is the second therapeutic drug candidate. So we again plotted these results graphically for easier visualization, which you can see here. So it might look surprising at first, but the NS means that there are no statistical significant differences between the ratios of vehicle-treated versus NEO2734 treated tumors. And while this result might seem kind of surprising, it was actually really expected because, as we know, NEO2734 as a drug inhibits the bromodomain of the protein complex that we're looking at, not the hat domain function, which is what's actually being measured by these ratios. So no differences here, but I just wanted to show it for visualization. So this third Western blot has, again, all of the same rows as the previous ones. And the difference here is that now the control-treated tumors are being compared to the dual-treated tumors. So we again plotted these results graphically, and this is the first time that we've seen 3 stars. And this now means that the p-value is less than 0.001. And this means that there are statistical significant differences between the ratios of vehicle versus dual-treated tumors. So the key takeaway here is that the dual treatment is extremely effectively inhibiting the P300 and CBP hat domain, which is a very positive result. So this final Western blot, which is arguably my favorite, has all of the same rows as the previous ones. And the difference here is that the A45 treated tumors are now being compared to the dual treated tumors. And the reason why we ran this Western blot is because the A45 drug and the dual treated tumors were the 2 experimental groups that were significantly different from the vehicle treated tumors, which is the control. So we again plotted these results graphically. And you can see 3 stars again here, which means that the p-value is less than 0.001. And this means that there are now statistical significant differences between the ratios of A45 treated versus dual treated tumors. And the key finding here is that the dual treatment is far more effectively inhibiting the hat domain than the A45 drug alone. So overall, we can now basically tell that A45 does not fully inhibit the hat domain, but when given in combination with the other therapeutic drug candidate, it becomes a significantly more effective hat domain inhibitor, basically showing the therapeutic potential of dual inhibition strategies. So these results indicate that inhibiting the hat domain function, which is evidenced by a loss of H3K27 acetylation, is very necessary to reduce ERBB2 mRNA levels. However, these ratios alone cannot serve as a clinical readout of either drug's ability to actually achieve these outcomes in vivo. So moving forward, additional biomarkers which reflect other functions of these proteins, such as the bromodomain, may be needed to monitor the anti-tumor responsiveness of both drugs. And then additionally, as you can see on the screen, newer, more potent hat and bromodomain inhibitors are currently being assessed in vivo in the Benz lab for their therapeutic potential, again using the mouse xenograft model, which you saw throughout this study. So the purpose of this new study is to re-examine if dual inhibition is really necessary, or whether a single, more potent domain inhibitor would actually suffice. So ultimately, continuing to investigate the effects of anti-ERBB2 therapeutic candidates will just provide further insights into the advantages of individual versus dual treatment options, and inducing nuclear ERB2 mRNA decay as a strategy instead of targeting the ERB2 receptors directly is a very promising approach that could transform the lives of many women and individuals diagnosed with HER2-positive breast cancer. So I want to extend a huge thank you to all of my amazing mentors in the Benz Lab at the Buck Institute. I think I saw Anna walk in. Thank you so much for coming. And yeah, just to my MARC classmates, Amy and Emily, I'm so grateful for this experience. And here's some photos of my time interning at the Buck Institute for you to look at, and I probably have time for like one question.
How do they target the target RNA with those inhibitors? Isn't it a risk that these inhibitors do not attach other RNAs?
Yeah, so basically the way that this mechanism works is that, hold on, let me go back to the slide, which will be easier for visualization. Sorry, there's a lot of slides. Okay, yeah, so you can basically see here that the key difference between current therapies that are on the market and are basically leading to treatment resistance in people diagnosed with HER2-positive breast cancer is the fact that they all target the ERB2 receptor on the cell membrane. But this new approach that we're working with in the Benz Lab basically inhibits that protein expression pathway much earlier on, and it targets the mRNA within the nucleus. So of course, there are risks associated with this, as there would be with any like novel transcriptional silencing approach. But yeah, that's basically the way it differs from current therapies, and is really promising at this point based on the results that we've gotten so far.
All right, thank you, Eloise. Thank you all so much for coming. Can all 8 MARC students just stand up so we can give you a final round of applause? Great. That's it. Get in touch if you want. We'd love to continue the conversation. Thank you for coming. Have a great night. MARC students, we're going to take